Anas. I will try to stick to the time. So, what I'm going to talk about is about a simple but overlooked idea that the buildings basically do not experience a stable future. And it's more important now than ever. I would like to say that this is the work of my student Avinash, Myakal, and an MSc thesis from him in a project in also collaboration with Anne Francis, who's also in the room. So the idea is the components age, HVAC systems lose efficiency, and climate around them also change. Yet, many of our retrofit decisions are still based on some of the static future assumptions from a particular climate case or a particular kind of like climate profile. So, in this work, we ask, can we generate more realistic long-term energy trajectories by integrating the climate projections, different ones, into a building simulation and building simulation into one automated workflow. I think I don't need to say more because we experienced one heat wave in Europe in June. And as I was looking at the news, there's one coming next week. And most of us know that our buildings are not made to withstand the heat. But now we are looking at retrofits. So should we do it the same way, or should we also think about all this kind of like problems? That means a retrofit decision is not just a short-term engineering decision. It should be a life cycle decision, as most of our buildings have ages from 60 to 200 years. Problem is that many energy assumptions simplify the future. They assume fixed weather files, fixed insulation process, performances, and fixed HVAC efficiency. But the climate warms, as we all know. The insulation performance is not ideal because it was not built for this heat, so it is starting to degrade faster. Some of our mechanical systems isn't designed to operate at this if problem. In the Netherlands, most of us have mechanical ventilation. The moment it goes over 26 degrees, we could already see it's not working anymore. And we don't need to start from scratch, right? Literature already gives us a lot of building blocks: life cycle cost studies, life cycle energy studies, climate studies on from the environmental domain, which is looking at future weather matters, degradation studies, which shows that materials change. We have digital twins. We have seen a lot of digital twins in this presentation in the last 2 days itself. So we do have all those. And we did look at all those and was kind of like looking at the limitations as well. The main problem is most of these approaches either use fixed energy savings kind of things using decadal snapshots or limited time horizons, or bespoke scripts that are hard to scale. So the gap is not that we lack individual models. We do have a lot of those and really good ones. But what we don't have is that they're not connected in a reusable, automated way that produce annual trajectories over full operational life of buildings. That is the missing bridge that we are trying to address in this presentation or in this study. So the aim is to develop and demonstrate a multi-model building energy consumption simulator, or what we call MMBEX. The contribution is not a new climate model, not a new degradation model or a new energy plus engine, but it is in the integration. How can we integrate all of those in a containerized, modular, and tool agnostic workflow that connects validated submodels and produce annual trajectories? For that, we use the XLRM workflow to structure it. So XLRM is we could have different external uncertainty, different kind of interventions, which are called the policy levers. And we kind of have performance metric to compare between the different ones. And in between is the R box, which is a physics-based energy simulation, which has multiple aspects. So uh, the idea here is we use this framework. The metrics that we are using is annual site energy, heating and cooling loads, and also cumulative savings. And this makes the framework useful for decision analysis, not just technical simulation. So I can tell this is a policy that I'm going to use and what is the outcome, and I could compare them. And the multi-model architecture that we developed is based on something called multimodel.nl, developed at TU Delft. I have a link to that later. So it connects three sort of models for this study, but it can be expanded because this is very modular. So the first container, second container, third container, all of those things, you could add like 10 more containers on this, depending on the type of simulation. Right now, it is linear connected. It could be co-simulated as well because we have a orchestrator workflow using Apache Airflow. So for this work, we connected we had the Codex climate projections, three of them, RCP 2.4, 4.5, and 8.5. Then envelope and HVAC aging was kind of like added into this simulation. Then we also had like Energy Plus as the annual simulation. It's automated through Docker containers, REST adapters, and Airflow orchestration. So we tried 28 scenarios, which is basically 3 climate scenarios, as I told earlier, but with different kind of maintenance, no maintenance, replacement, regular maintenance, etc. So we could do that. So those are the policy levers, whether I maintain continuously or I replace twice. So what is my strategy? And it's also connected to a lot of cost and other aspects. So scenarios actually range from baseline to comprehensive strategies and regular maintenance. Now, what I'm going to show next is findings, but I'm not going to say that's the perfect findings, but this is just findings to show that we can get insights when we connect all these together. So the first findings is actually the rationale for the study itself. So it's almost a confirmation of our assumptions that the baseline result, what we are seeing here is showing why static modeling is risky. Because already you could see much more peaks over the years. And the total energy consumption increases by about like 43% over the 60-year horizon. So when you start like at the start and at the end of the 60 years, there's already 40% increase. And there is a lot of intra-decadal volatility. And it could also be driven by extreme climate. So we don't have the, outliers in here, but this is the normal projection that we get from the RCP 8.5. And for retrofit planning, this matters because our systems, the building systems, it shouldn't be kind of designed for averages alone because they also need to perform under these peak years. We also tried comparing different types of scenarios, as I told, retrofit, regular maintenance, etc. And one of the most practical, interesting results was that a single HVAC replacement in 25 only saves about 8%, while regular maintenance has a savings of energy about 10%. So we think replacing is better, but often it is not. It is maintaining that's much more better. Because that 10.4 is even compared to the dual replacement, that is, we replace twice. The combined strategy, if you are replacing and maintaining, gives us only slightly better kind of like savings. That's around 13.6%. The key message is that early and consistent maintenance can capture a large share of benefit while also reducing the volatility, because you could see in that scenario, it's a bit more smoother. And this is very important for facility managers with limited budgets. So what did we do in the study that is important? So it contributes a practical step with the multi-model framework toward climate-aware life cycle retrofit planning. It shows how validated submodels can be integrated in these kind of like scalable workflows. And for practice, it helps compare when to maintain, replace, and retrofit. So we studied this on office building. I forgot to say that earlier, in Delft. And the whole case study was around Delft. And for us, the next steps are also important by linking this to life cycle cost, environmental assessment, adding a little bit more of like monitoring and calibration workflow to make it like into a digital twin system, so that some of the assumptions that we make could also be validated or the models could be updated. And also moving towards, so here we have the RCP and all of those things, but our simulations are almost deterministic. So we want to go to probabilistic ensembles later. But what this study gives us is that retrofit planning must treat buildings as changing systems in a changing climate. So with that, I conclude the talk. Uh, on the left side, you could have more information, all the GitHub repo of our prototype and the technology. So you could replicate it yourself. It's in Docker containers. On the right side, there is a bit more information about how this all works within the master thesis. That's all from me. Thank you. And that was 10 minutes, 20 seconds.